A magnitude 4.2 earthquake just struck directly on top of one of the most dangerous fault intersections in North America. And if you understand what this location actually is, this is not a normal Tuesday earthquake. This is a needle moving on a fault system that has been loaded, locked, and waiting for decades. Here's what happened. On July 12, 2026, a magnitude 4.2 earthquake struck near Fraser Park, California, at a depth of about 13 kilometers. On its own, a 4.2 is nothing special. California gets earthquakes this size on a regular basis, and most of them come and go without anyone outside the immediate area even noticing. But location is everything in seismology, and this one did not hit some random patch of desert. It hit almost exactly on the point where the San Andreas Fault meets the Garlock Fault, the single most geometrically significant junction in Southern California's entire fault network. If you pull up the USGS earthquake map for this region, you can see it immediately. The San Andreas runs up through Southern California as a long sweeping line, and right around Fraser Park it bends. That bend is not a coincidence, and it is not cosmetic. It's the point where the Garlock Fault runs into it from the east. Two major fault systems intersecting like that creates a geometric pressure point, the kind of spot where strain has nowhere clean to go, so it builds up instead. When you get a bend in a major strike-slip fault, that bend becomes one of the most strain-concentrated locations on the entire structure. And the numbers back this up. Looking back through the seismic record for this specific stretch of the fault junction, this 4.2 is one of the strongest earthquakes to strike exactly on this location in at least 26 years. There have been other quakes nearby, a couple of magnitude 5s to the north and south over the last 2 decades, a scattering of magnitude 3s. But almost nothing has landed precisely on the junction itself. This one did. Let's talk about why that junction is so dangerous in the first place, starting with the Garlock Fault, because most people outside of California have never even heard of it. Now pair that with the San Andreas itself, which needs no introduction. This is the plate boundary fault that defines earthquake risk in California, a right lateral strike-slip fault, capable of magnitude 8.0 or greater in its southern segments. The historical record along the southern San A. Andreas is honestly kind of eerie once you start lining up the dates. On December 8, 1812, a double earthquake sequence struck the region, a 7.5 followed by a 7.1. Then, in 1857, the Fort Tejon earthquake ruptured the San Andreas at an estimated magnitude of 7.9, one of the largest ID earthquakes ever recorded in California history, with rupture believed to extend close to this very junction area. San Diego took a 7.4 in 1800. These aren't ancient legends. This is documented seismic history from a fault that has produced repeated magnitude 7+ events, and it has not done so in the modern era anywhere near the scale of Fort Tejon. So when I say this junction is overdue, I'm not being dramatic for the sake of a headline. Both faults meeting at this point are independently capable of magnitude 7.5+ earthquakes. Both are showing large multi-decade or multi-century gaps since their last major rupture, and now we've had a distinctly placed magnitude 4.2 land almost exactly on the intersection. It's worth sitting with that 1857 Fort Tejon rupture for a moment, because it's the closest thing we have to a preview of what a full San Andreas rupture near this junction actually looks like. The fault slipped along a rupture length of well over 300 kilometers, with displacement estimates in places reaching close to 9 meters. Structures shook as far away as Los Angeles, and the ground motion was reportedly strong, enough to be felt across a huge swath of the state. That earthquake occurred in a California that had a tiny fraction of today's population and infrastructure. A repeat of Fort Tejon today, on a stretch of the San Andreas running near major highways, aqueducts, and population centers, would be an entirely different order of disaster than it was in 1857, simply because of how much more is now built on top of and around that fault line. The 1952 magnitude 7.5 earthquake near the Kern County area is another data point worth understanding properly. It struck at a shallow depth of around 6 kilometers, and is still considered one of the largest earthquakes to hit California in the last century. Importantly, it didn't rupture exactly on the San Andreas. It occurred nearby, associated with the broader fault network in that region rather than the main trace itself. That distinction matters because it tells us the area has produced major magnitude earthquakes adjacent to this junction without the junction itself going. In other words, the surrounding system has proven it's capable of producing 7.5 class events. The main junction just hasn't been the one to do it yet in the modern record. Let's talk about what's been feeding stress into this system recently, because this earthquake didn't happen in isolation. In July 2019, 2 major earthquakes struck near Ridgecrest, California. A magnitude 6.4 foreshock followed the next day by a magnitude 7.1, the strongest earthquake to hit California in 20+ years at that point. Ridgecrest sits in the East California shear zone, a broad zone of faulting to the east of the Garlock. Post-earthquake stress modeling from seismologists F, following that sequence, estimated that the ridge crest rupture increased stress on the Garlock fault by roughly 30%. Think about what that means. You already have a fault that's known to be locked, overdue, and capable of a 7.5 plus rupture. And then an entirely separate nearby earthquake sequence shoves another 30% of stress onto it. That's not a small footnote. That's the kind of stress transfer that seismologists take seriously when assessing which fault might go next. And the ridge crest sequence isn't the only recent activity worth flagging. Earlier this year, a magnitude 5.7 struck near Silver Springs, Nevada, just outside Reno, part of the Walker Lane system, a corridor of faulting that runs parallel to the Sierra Nevada and helps accommodate the shear between the Pacific and North American plates as it moves through Nevada B, before handing off into California's fault network. Then, on June 24th, a magnitude 5.6 struck between Ukiah and Willits in Northern California, right along another bend in the San Andreas system, and by the historical record, the strongest earthquake known to have hit that specific area. This is a section of the fault that typically shows very little seismicity, and suddenly it produced a historically notable event. Zoom out further and the picture gets even more interesting. A magnitude 7.0 struck off the coast near the Triple Junction in December 2024. A significant sequence hit near Cuba in the Gulf region, felt as far away as Florida. Worth noting, because seismic energy from distant large earthquakes can and does load stress onto faraway faults. That's a well-established phenomenon in seismology, not speculation. On that same general timeline, a major double earthquake sequence, a 7.5 followed by a 7.2, struck the Bonoco Fault region in Venezuela, one of the most destructive seismic disasters that region has seen in generations, with tens of thousands of people still unaccounted for and thousands of confirmed deaths. A magnitude 6.1 followed near Cuba. A magnitude 6.0 struck down in Baja California, a region with documented historical linkages to seismic activity further north in California, even if the connection doesn't hold every single time. None of these events are freak accidents happening independently of each other. Plate boundary systems are connected, stress transfers across distances, and when you start stacking up this many notable events across a relatively short window, Nevada, Willits, the Gulf, Venezuela, Baja, and now a fault junction earthquake at Fraser Park, it paints a picture of a broader system that is actively redistributing stress, not one sitting quietly in equilibrium. It's also worth understanding how seismologists actually think about stress transfer, because it's not just a hand-wavy concept, it's something that can be modeled. When a fault ruptures, it doesn't just relieve stress on itself, it redistributes stress in the surrounding crust, increasing pressure on some nearby fault segments while decreasing it on others, depending on their orientation relative to the rupture. This is typically visualized using what's called a Coulomb stress transfer model, which maps out zones of increased and decreased failure likelihood around a rupture. The 30% stress increase attributed to ridge crest's effect on the Garlock isn't a rough guess pulled from thin air. MES from this kind of modeling, cross-referenced against the geometry of the fault and the size and orientation of the ridge crest rupture itself. When multiple independent earthquakes in a region are all loading stress onto the same target fault from different directions, that target fault effectively becomes the focal point of the entire regional system, whether or not it's the one making headlines yet. Let's get into the mechanics of what actually happened at Fraser Park, because the details of this specific rupture matter. There are 4 basic types of faults. A normal fault is extensional. One block drops down and away from the other, and the crust stretches and gets longer. A reverse fault is the opposite, compressional, with one block thrust up and over the other, shortening and thickening diastole, crust. Then you have strike-slip faults, where blocks slide horizontally past each other with no significant vertical motion. Right lateral strike-slip means that if you're standing on one side, the other side moves to your right. That's the San Andreas. Left lateral is the reverse. That's the Garlock. The focal mechanism for this 4.2 shows a strike-slip rupture with a minor normal extensional component, meaning there was a small amount of stretching alongside the horizontal slip. Because the epicenter sits so close to the exact junction point, it's genuinely difficult to say with confidence whether this event ruptured on the San Andreas side or bled over onto the Garlock side of the intersection. But the extensional component is worth noting because it lines up with the actual geometry of the junction. Picture the Garlock coming in from the east as a left lateral fault, essentially pushing into the S, and Andreas at an angle. That collision is exactly what produces the bend in the San Andreas that we see on the map. And a bend like that, under ongoing strike-slip motion, naturally creates small pockets of extension right at the kink. That's consistent with what this earthquake's mechanism shows. So where does this actually leave us? To be clear about what a magnitude 4.2 can and can't tell us, it cannot predict when or if a larger earthquake will follow, and no legitimate seismologist would claim otherwise. Earthquakes cannot currently be predicted with precision on a live forecast in terms of long-term probability. What a magnitude 4.2 in this exact location can do is confirm that this fault junction is active, that it's capable of producing measurable rupture right at its most strain concentrated point, and that it's happening inside a broader window of elevated regional seismic activity. T. That's not nothing. That's the kind of signal seismologists watch closely, because both faults meeting here are independently overdue for major ruptures, and this event sits right on top of where they connect. There's also a longer-term pattern worth mentioning. Over long timescales, seismic activity along Southern California's fault systems has shown a tendency to shift back and forth between network, sometimes across periods measured in decades. Recent big ruptures, Ridgecrest in 2019, the events further east through the Mojave, have concentrated in the eastern shear zone. If that pattern holds, there's a real possibility that the next major event shifts back toward the west, potentially involving the Garlock directly, or the southern San Andreas, or Consau. Inevitably, both in close succession, though a simultaneous dual rupture remains a less likely scenario than either fault going independently. And Southern California isn't the only region carrying risk right now. That magnitude 5.6 near Willits and Ukiah is a reminder that Northern California has its own overdue faults, and the Bay Area in particular has multiple systems that are considered ready for a major rupture. The Hayward Fault chief among them, along with the Green Valley and Calaveras faults. It's also worth remembering that not every dangerous fault is even mapped. Yet, the West Napa Fault was essentially unknown until it produced a magnitude 6.0 earthquake in 2014 and revealed itself to be connected into the broader regional fault network. California's hazard picture isn't limited to the faults we already have names for. So here's the actual takeaway without the hype. A magnitude 4.2 earthquake struck almost exactly on the junction of the San Andreas and Garlock faults. Two systems independently capable of magnitude 7.5 or greater both show. Long gap since their last confirmed major rupture, and one of them, the Garlock, sitting under roughly 30% additional stress following the 2019 Ridgecrest sequence. This event doesn't tell us a major earthquake is imminent in the next hours or days. Nobody can responsibly say that. But it does confirm that this junction is mechanically active right now at a moment when the broader region, from Nevada through Northern California and down through the Gulf and into Baja, is showing an unusually active stretch of seismicity. That combination is exactly what seismologists mean when they talk about a fault system that's unlocking. If you live in California or anywhere with meaningful earthquake risk, this is a good moment to actually check your preparedness rather than just think about it. Have a go bag ready with basic supplies: water, food, a first aid kit, sturdy hose, and a flashlight. A hand crank or battery radio is worth having, so you can get information if cell networks go down. Consider a backup power source, like a portable power station. And if you want to go a step further, a small portable solar charger, so you're not fully dependent on stored battery power if the outage runs long. Know your building's exit routes, know where to shut off gas and water if needed, and make sure everyone in your household knows the plan before you ever need it. A few things people consistently overlook when they put a kit together. First, water. The standard guidance is 1 gallon per person per day, and you want enough for at least 3 days, ideally more, given how long roads and utilities can stay disrupted after a major event. Second, cash. If power and networks are down, card readers won't work, and having small bills on hand can make a real difference in the first 48 to 72 hours. Third, copies of important documents, identification, insurance information, emergency contacts, kept somewhere or proof and easy to grab. Fourth, don't forget medications. If anyone in your household relies on a prescription, keep a few extra days' supply rotated into your kit. And finally, secure heavy furniture and top-heavy items in your home because in most earthquakes, falling objects cause far more injuries than actual structural collapse. If you're in a multi-story building, know your fastest route to an exit, but also know that during actual shaking, the advice is to drop, cover, and hold on rather than trying to run outside. Most injure. Rise in earthquakes happen from people moving during the shaking itself, not from staying put under something sturdy. Practice this with your household so it's automatic rather than something you're figuring out in the moment. I'll keep tracking this fault junction and the broader regional activity as it develops, and I'll bring you updates the moment there's anything meaningful to report. Stay safe out there, stay prepared, and I'll see you in the next one.